Okay, so the next scenario we're going to look at is again the step. The step is smooth, so not abrupt. And now we have supercritical flow. So the upstream flow at section 1 at the water level is located here. And let's say we have a depth of y1, which now is supercritical flow. The previous case was subcritical flow at section 1 or transect 1. Okay. The same assumptions. We're going to assume there's no head loss, short distance. The energy grade line is constant because there's no head loss. That's EGL. And obviously, this will be our total energy upstream. So this will be E1. Okay. Now we're going to transfer the data from this chart to our EY graph, which is on the left. So that's our depth. Let's find out depth. That's the depth we have. And this is the corresponding specific energy at section 1, which is E1. So that's the point. And let's just keep continuing this to get Y1. Okay, the step has a height of delta Z. That's delta Z. And after the step, we get to section 2, and we want to find out where the water level is going to be, what is going to happen to depth, and so on. At section 2, just like before, total specific energy will be this much, E2, and it is obvious that E2 is equal to E1 minus delta Z. Again, specific energy is defined with respect to the channel bed. So if the channel bed goes up, specific energy goes down, assuming there's no head loss. EGL is constant. Okay, so let's again transfer section 2 to our EY graph. And if we do that, section 2 will be, let's say, somewhere here. That is E2. The distance between these two is delta Z. Again, obvious on the chart. And the question here is, intersection of E2 and our EY graph gives us two possible points for depth. One is down here. Let's call this one Y2A. And another one up here. Let's call this one Y2B. Okay, so which one is the answer? Which one is the depth of flow downstream? Just like what we said, there's a couple of ways we can go from point 1, which is our starting point, that's point 1, to point 2A or 2B. Let's focus on 2B for now. How do we get from 1 to point 2B? One way is just jump across and go like this. We talked about this one. This is not possible because along this orange path, the points are away and off the black EY graph. That means this charge has to be different on these graphs. That's not possible. So remember, this is for a constant Q. As long as this charge is constant, we have to stick to this black line. We have to stay on this black line. So this path is out. It's not possible. Okay, what is the other path? The other path is stick to the EY graph and just follow along and go to 2B. So let's do that. If you do that, we're going to do something like this. Go along and get to 2B. Now, a couple of things happen here. We see that we obviously pass through 2A. Okay, let's keep that aside for now. And then we pass through the critical point, which is right here. So that's the critical point. And as we said before, for critical flow to form, we need some external changes. We need abrupt changes in geometry. That's the most common case. We don't have that. We assume our step is smooth and gradual. So this path is also out. This is not possible. In other words, we cannot go from 1 to 2B so far based on the assumptions we've made. So 2B is not possible. 2A is the answer. So let's again transfer this back to our longitudinal section of the channel. We're going to get a depth that's this much, let's say. That's Y2. That's depth downstream. And because the transition, the change in geometry is gradual, it is reasonable to assume that the change in water surface will also be gradual. So something like this. Water level will slowly go up and get to Y2. At section 2, now a couple of things happen there. Section 2, we see that on the EY graph, E2 is, Y2 is greater than Y1. So actually, I should say Y2A. So depth is greater. And for a given fixed energy, it is, again, reasonable to assume that this will correlate to a smaller velocity. So depth goes up, velocity goes down. But at section 2, flow is still supercritical flow. How do I know? If you notice on the EY graph, point 2A is also on the lower branch of the EY graph. Lower branch is supercritical. So the flow regime did not change. Supercritical upstream, supercritical downstream, just like what we had in the subcritical case. The major difference, if we compare side by side, is that in subcritical flow, depth reduced. In supercritical flow, depth actually increased as we went through the step and had the a step in the flow. Okay, so far we looked at relatively small, I should write it here, small steps. So delta Z is relatively small. What does it mean, and what are the other cases? What are the other scenarios? So let's look at that case. The same story, we have delta Z, that's the height of the step. Okay. And we have flow approaching this step. For now, it doesn't really matter, but let's assume it's subcritical. It's not going to change what we're discussing. And we're going to see what happens in this case. Now delta Z is not small. How big is it? We're going to talk about it in a second, but let's assume that that assumption we had is not applicable anymore. We have a couple other assumptions still there. For example, we're going to assume that the channel is rectangular, no changes there. And because of that, again, if you remember, in our basic definition was that the unit discharge is total discharge divided by the width of the channel. So here, point A or point 1 upstream is located somewhere here. So let's say this is our specific energy, and that will be our depth upstream. Let's call it Y1, which is this much, right? And now we're going to look at the height of the step and kind of translate it side by side, translate it to changes on the EY graph. If you remember, what we said was that as you bring the channel bed up, you put a step, delta Z goes up, the specific energy goes down because you're moving your datum closer to the total, which is your specific energy line, EGL. So as we move up in terms of channel bed, specific energy reduces. So for different values of delta Z, we're going to have different E values, one here, one here. And at some point, we're going to get to this point, which is the interesting one. We're going to get to a point where, I'm going to delete the other ones, our specific energy is now right at the critical point. Remember, this is the vertex is the critical point. So as we increase delta Z, we get to a point where our specific energy becomes minimal. Remember, critical energy is equal to or is the same as the minimum energy. It's obvious on the graph, right? This height of the step required to get to the minimum specific energy is a couple of terms we call it is the delta Z max, maximum step height, or sometimes we call it the delta Z critical. I'm going to write it here too, delta Z critical. In other words, this is the maximum height of a step that you can put in a flow to get down to minimum specific energy. On the EY graph, it's obvious. We can't go past that point because there's no point to the left of the EC line that we have. So what happens at point C or the critical point is that, so at the critical point, at 2, at section 2, because that's where we are, right? This is equal to E2. We have critical point. And this translates to critical depth. So in this case, the difference between what we have now and what we saw before is that Now we have a step height, delta Z, that puts us right at the critical point, the specific energy. In other words, depth will become equal to YC. Y2 will be equal to critical depth. So it will be, let's say, somewhere here. The same story is gradual steps, smooth steps, so gradual drop in water level, something like that. But depth, it will end up being critical depth. And if you remember, we talked about calculations of the critical depth. I'm going to rewrite them real quickly here. YC was equal to Q squared over G cube root. And also EC or E min is equal to 3/2 of YC. So if we have Q, small q, we can compute YC because YC is a function of Q and G. And then if we have YC, we can compute EC. So a typical type problem or situation is where we say, okay, we have this type of flow. How big can the step be before we get to the, or we get to exactly the critical point? So we can use Q to calculate YC, then use that to calculate EC, and then delta Z, I'm going to write that down here. Delta Z max or critical will be equal to whatever you had upstream minus the minimum specific energy. So this will be a key equation to use for that kind of problem, right? Or it could be the other way. It could give you delta Z max and E1 and calculate, but the same idea. So the point is, as you keep raising the bed elevation by putting a smoother step, you keep doing that, and you keep moving left on the EY graph. And as at some point, delta Z will be such that as you move to the left, you end up right at the critical point. Your specific energy at the new station or section downstream, which is upstream minus delta Z, E at upstream minus delta Z, will put you right at the critical point. And that is also, remember that that's the minimum specific energy. You cannot have any E less than that for the given discharge. So this is where we end up with the kind of the vertex of the graph. And in terms of calculations, if we have discharge, we can calculate YC. And if we have YC, you can calculate EC or E min. And the difference between your upstream E and E min is delta Z max. So that's the biggest step you can put in the channel or raise the channel elevation without causing other issues, which we'll look at. We'll look at that later, right? So to kind of summarize this, so we started with upstream water level up here, and this translated to a depth of Y1 upstream and specific energy of E1, again, energy upstream. And we moved to the left by how much? By this much, so that we end up at EC. What is that distance? Is delta Z max. And at the critical point, depth is exactly YC. All right, so delta Z max is here. And depth downstream is here, and it's equal to YC. And again, because we have a gradual step, smooth step, water level will translate very, very gradually. Okay, so let's summarize the equations. We have upstream energy, specific energy is equal to E1 plus Q squared 2G Y1 squared, nothing new. E2 will be equal to EC or E min, and it's equal to, again, we've seen this before, 3/2 times YC. And what is YC? YC is, let me write it here, YC is equal to Q squared over G cube root. So if you plug this in here from these two, then we can plug in and calculate delta Z max, which will be equal to E1 minus EC or E min, the same idea. And again, the concept definition or the meaning is that this is the minimum height of a step that you can put in a channel. Now, I'm going to briefly mention the next topic, and then we're going to stop and then continue next time. But somebody might say, okay, what if we actually do this, but we put a bigger step than delta Z max? So I'm going to sketch a small EY graph up here. That's EY, and this is what it looks like, let's say. And we started upstream with E value of this much. And let's say we put in a step, but the step is too big. It's bigger than delta Z max. So our delta Z is actually greater than delta Z max. So the question is, what happens now? So if we do the calculations again, E2 will be here, and it will be equal to E1 minus delta Z. But now there's actually no intersection between E2 line and the EY graph. And what's happening here? How do we deal with this, this situation? This is a scenario or fluid condition that we call choking. What is happening and what it means is that the channel as is does not have enough energy to pass the discharge over this hill, this big step, which is not a step anymore. It's a big obstruction. So the flow is really choking. That's what it comes down to. How do we deal with that? How does the flow deal with that? Do we need to do anything specific? We don't need to do anything, but the flow will adjust and we'll make some changes to the flow, approach flow, and so on, so that we manage to get past this obstruction. And the very first and obvious reaction that we expect to happen is that the flow will kind of back up and fill up upstream, and at some point, depth will go up, and then we'll go over the step. But what is the hydraulics? What are the hydraulics happening there, and how do we study that? That will be our next topic, which we'll talk about. But this is again just for now. Let's be familiar with the term that this is a open channel flow choking scenario where the step height is greater than delta Z max.